Hi, I'm George and I'm making some double E videos. So, what is it that we're looking at right here? Now what we've got is a CTLTI that represents an LCCDE, or that's expressed in that way. And what that is basically a differential equation. So we have this diffie-Q problem that represents our system, right? So as you know, with a system you have some x of t, which is convolved with some kind of unit response, which gives you your output, or y of t. So we have our output on this side and our input here, and it's asking us in part A here to find h of j omega and h of t, or the unit impulse response or frequency response in the frequency domain. And then what the problem then asks us to do is to take that value, that response function, and give us our new output if we change the input from this 2 times x of t to this exponential expression here. So first thing we're going to do, or the first thing we need to do, is find h of t, right? And so, you could try to take your output and your input and perform some kind of inverse convolution, but it's a lot easier to just take this, and instead of worrying about convolution at all, and to move to the frequency domain, where everything is just simple multiplication and division. And when you're dealing with a differential equation like this, there's a trick to it. So, just like with Laplace transforms, we're going to replace our double derivative and our single derivative with a variable squared. In this case, because we're in the frequency domain, it's j omega. Our functions are just going to be represented as constants. And the trick to this, and you may remember this from differential equations, so our input is going to be in the numerator of a fraction that we're going to write, and the output is in the denominator. And so what does that mean? Or what that gives us then is going to be h of j omega. So I'm going to write this as h of j omega. It equals 2, because we've got this 2x of t, over, and I'm just going to be rewriting this expression here on the left in our j omega form, which is j omega squared plus 6j omega plus 8. And it's that easy. Now, this fraction, you really can't do a whole lot with that fraction. There's not much you can do to bring it kind of in line with anything that you can easily bring back into the time domain. So what we're going to do is if we go over here to this table of Fourier transforms, you can see right here, when you're dealing with fractions, you have these 3 universal expressions that will transform us into these exponential forms of in the time domain. And so our goal is to make something that looks like this, right? So if we go back here, and we can see that this breaks down into something that's factorable, or into something with factors. So we end up with 2 over and j omega plus 4 times j omega plus 2. This is closer to what we want. It doesn't quite look like, it's not quite in this form yet, but we can get it there using something called, and you may remember this from diffie-Q, called partial fraction decomposition. Now, if you need a refresher for how this works, I'll go ahead and work through this with you right now. So this fraction, we're just going to take this guy, and we're going to split up the 2 factors on the bottom, and we're going to put them under a constant. So this is some a over j omega plus 4, plus some b over j omega plus 2, right? So we're leaving this with an equal sign here, because the next thing we're going to do is we're going to take this bottom half, and we're going to multiply it into the right side of this equation here. And I'm just going to work through all the algebra so that we can get a feel for it, that we end up with 2 equals a over j omega plus 4, and I'm going to go ahead and cheat, and I'm going to copy this, copy and paste, bam, to wish your notebook did that, plus b over j omega plus 2 times the same thing. So basically, what I did is we had this fraction, and I just distributed the denominator of the left side onto the right side, and you can see that these guys cancel out, these guys cancel out, and you just end up with a times j omega plus 2 plus b times j omega plus 4. Now, you know, you don't have to go through all these steps to do this. You can see, just looking over here, that, you know, this guy ends up here, this guy ends up here, and you can just, you know, skip these steps. But I'm just working through this in case just in case some of us need a refresher, like myself, as far as how this works. Now, the next thing we're going to do, so this is still equal to 2, right? So what we're going to do is something, I learned this in my differential equations class, but we're basically going to distribute our constants here, and then we're going to split this up into two separate equations, but that are based on the same base equation, right? So we have aj omega plus 2a plus bj omega plus 4b equals 2. And you can see here that, and I'll just write this in green, that we have a 0 j omega here. Now, there's a law in algebra that says that if you have some, you know, we have j omega, j omega, j omega, right? And then we have another set of numbers that's constants, right? So if we call everything in blue is x of, we'll call it g of j omega, and everything in green is h of j, well, we're already using h, we'll call it f of j omega, then we know that the function that we want to get, we'll just call it, you know, capital F j omega is equal to g plus f, lowercase f. Right, and using this property, we can basically turn this equation here into two separate equations, and we can take our two unknowns, a and b, and solve for them, you know, as a set of as a linear system. So we'll go ahead and split them up. We're going to say that a j omega plus b j omega equals 0. We have 2a plus 4b equals 2, and that's important. You don't want to forget that constant. Now, so we have this set of equations. We can just remove these j omegas. We just end up with a plus b equals 0, and we can see that a is equal to negative b. And if we take that and plug it in down here, we can see that 4b minus 2b equals 2. Therefore, b equals, so we're just going to subtract 2 and then divide by 2. B is equal to negative 1, right? And you can see that because if you take this guy and you do the algebra, you can see that you end up with negative 2b, or, I'm sorry. You know what? B equals 1, not negative 1. That's what happens when you skip steps, right? You end up with 2b equals 2, b equals 1. So, and that's what happens when you skip steps. Now, and you can see from here that a is equal to negative 1. There you go. So we just take these values and we plug them back in, and we end up with, let's see here, a is 1, negative 1, b is 1. So we come all the way back here, and we say that it is equal to, and it's we'll just go ahead and put b first, 1 over j omega plus 2 minus 1 over j omega plus 4. Simple enough. Alright, so that is h of j omega. But we're not done. See, we now need to find the unit impulse response, right? So we need to find h of t. Now, we have this in a form that we can do an inverse Fourier transformation and get some like expression in the time domain back. So what we'll do is, looking back at this table here, you remember that we were trying to get things into this form here, and we can use this expression right here to, for these values in the frequency domain to get this in the time domain. So what we're going to do is we'll go back over here. So we can see that in the case of this expression here, a is equal to 2, a is equal to 4, right? These are all to the first power, which is going to be important later. So we know that if we do a Fourier IFT for inverse Fourier transformation, we know that h of t is equal to e to the negative a t, right? So that ends up being to the negative 2t times the unit step function minus e to the negative 4t times the unit step function. And that's it. This right here, that's a. So we just solved the first half of this problem. So this shows that even with the differential equation, without doing any kind of complex math, this was all algebra. We're able to take a differential equation in the time domain, move it into the frequency domain, and then solve it using simple arithmetic, and then bring it back into the time domain, just because we know some of these Fourier transformations. So it reminds me of Laplace transforms in my DPQ class, the process, but this feels a lot easier. Maybe it's because I have more experience now than I did then, but it is what it is, right? So now we have our h of t, and it asks us what happens, what we're going to get if we change our input, right? So we know, and we're just going to go back to basics here, that for an LTI system, if we have some x of t and we send it through some response function, we're going to get our output, right? So this is out, response, in. And if we do Fourier transformations, and I'm writing a double arrow because Fourier transformations can go either way. You get x of j omega, h of j omega, and y of j omega. Now, what's important here is that we know that this is convolution. X of t to h of, or x of t convolves with h of t to give you your output. But in the Fourier domain, in the frequency domain, it's multiplication, right? Simple multiplication. So we know that what we want to do is that instead of having to go through the process of doing convolution with these exponential functions and all of this craziness, we're just going to turn this, send it back into the frequency domain. We're going to do the same with our new input here, which I'm going to go ahead and copy right now, as a matter of fact. Copy. Okay. So we're going to go ahead and paste this here, and we're going to send this into the frequency domain. Now, looking at our table, that is not our table. Looking at our table, we know that we just take a, put it in the denominator, add j omega, and it's good, right? So, oh no, I missed something. This is multiplied by t, so that changes things right here. Okay, so now, because we're multiplied by t, we're looking at this right here. So t e to the negative at transforms into this expression where you have a square in the denominator. And that's all that t signifies, is that there's a square. If you have something more than just t, then you can end up with, and this is more of a general expression, this last guy here. But, so because we have a t, we end up with 1 over 2, because that's our value of a, plus j omega, the quantity squared. So this is our capital X of j omega. If we want our output, so we're going to multiply that by h of j omega. And so that gives us, and I'm going to write and make this an arrow here, h of j omega. And that is u. Whoop, oh, no, no. Is my tablet not going to keep up with what I want to do? Oh, there we go. All right. Copy. And paste. So, we have 1 over j omega plus 2, the quantity squared, times this expression. And that equals our capital Y of j omega. So what we have to do, we're going to distribute this, and then we're going to simplify, right? So we distribute, and we end up with 1 over j omega plus 2 cubed minus 1 over j omega plus 2 squared times j omega plus 4. There we go. So, now one thing you don't want to forget is this minus sign. When we get to the end of the problem, you're going to need to consider that. But let's look at this first. So, we have another fraction that, just like in part A, we can't just take this and it's not already in a form that we can turn back or send back into the time domain. So we're going to have to do our our partial fraction decomposition again. Now we have a squared term here on the left of our denominator, and we got to keep that in mind. So I'm just going to take this guy and I'm going to deal with it by itself. So we have 1 over j omega plus 2 squared j omega plus 4 equals, all right, and as a part of the partial fraction decomposition, we have a over j omega plus 2 plus b over j omega plus 2 squared plus c over j omega plus 4. Now you might be saying, hey, why do we have 2 j omega terms? And and so the reason is this is squared, and this happens when you have repeated roots in the denominator. You've got to have one fraction for each multiple of the root. So if this was j omega j omega plus 2 to the 4th, then you would end up with plus the 4 fractions, and it would be over increasing numbers of the root. and so that's how you would deal with multiple roots. The more roots you have, the more fractions you have, obviously. So let's go ahead and continue. Let's see. So we're going to go ahead and take our denominator here. We're going to distribute it or multiply it into the other side, and without spending time doing all of the algebra, we know that this is going to be a times j omega plus 2, j omega plus 4, plus b times j omega plus 4, because we have that double root at the bottom. Both j omega plus 2's are going to cancel out, plus c times j omega plus 2 squared, because the squared term will come in here, the 4's will cancel out, the end. And this is all equal to 1, because remember, we had the 1 on the left side here. So we have to make sure that we remember that constant, because it might not always be a constant. It might actually be some kind of expression, and we need to keep that in mind when we go to solve this. So I'm going to go ahead and simplify this guy. This ends up being, actually let me just rewrite it here. A times j omega squared plus 6j omega plus 8 plus b times j omega plus 4 plus c, and we'll go ahead and simplify this or expand this to plus 2 plus 4 j omega plus 4. Alright, this all equals 1. Now, we're going to go ahead and, now, rather than do the algebra, I think you have a pretty good understanding of how we break this up. You know, I'm sure that you've done it in previous classes and that kind of thing. So I'm just going to skip those steps and go straight to A plus C equals 0, right? Because we have A times the j omega term, j omega squared term, C times the j omega squared term. So we just have those two equal 0 because there's no j omega squared term on this side. So, next expression, 6a plus b plus 4c equals 0. Finally, we have 8a plus 4b plus 4c equals 1. Don't forget that constant. It's an easy way to, it's an easy mistake to make. Now, I'm going to go ahead and simplify. Easy to see that a is equal to negative c. Let's plug that guy in here. So, you know, if a equals negative c, then it stands to reason that c equals negative a. So we have 6a plus b minus 4a equals 0. And you can see, you know, we subtract, we have 2a. So we have 2a equals b, negative b. Alright, so if we plug both of those in here, we'll have 8a minus 8a, because if negative b equals 2a, then this guy, so we have 4 times negative 2a, negative 8a, minus 4a equals 1, because, as you know, this is equal to negative a. So, we do the arithmetic, and we see that a is equal to, let's see here, negative 4 is equal to negative 1 over 4. And so we plug this in up here, we can see that c is equal to 1/4. Plug this in here, so 2 times a quarter is a half, so negative 1/2 equals negative b. b equals 1/2. There we go. So we can take all three of these and plug them back in right here, right? So we have negative 1/4, 1/2, and 1/4. And we can take these three values and we send them all the way back to the expression that we were trying to simplify, right? So this is our answer, or our replacement for that. Now, one thing to keep in mind, and I'm writing, actually, let me rewrite this problem before we move on here. So let's see, this is y of j omega is equal to 1 over j omega plus 2 cubed. And so this is where the negative comes in important, right? So if we go ahead and distribute the negative now, this becomes a plus. This negative a becomes a positive a, this becomes negative, and this becomes negative, right? So we get positive 1/4 j omega plus 2 minus 1/2 j omega plus 2, the quantity squared, minus 1/4 j omega plus 4. Let's make sure I got that right. I did. Okay. Now, if you plug this fraction into like a TI-89 and hit expand, you know, it'll give you this. It'll give you these values, but it'll write them in a different way. You know, it'll call it like 1 over 4 times j omega plus 2, which is fine. The reason why I'm writing it like this is because you have to keep in mind what we're working toward, right? So if we look down here, you can see that the expressions that we're looking for are in the form of 1 over some constant plus j omega. You know, you can have some other number down here times everything, but you have to make sure you don't forget it when you do your transform. By writing it like this, you ensure that, you know, you don't forget it, that it's something that doesn't get lost when you do your inverse Fourier transform. Now, these two we can already do, right? We already know how to do this. So this is A, and this is just some constant. So we're just going to multiply it by what we get in the time domain. So it's 1/4 times e to the negative a t times the unit step function. Okay? And this is going to be a negative 1/4 times e to the negative 4t times the unit step function. Now, these other two are a little more complicated. We've already talked about this, or we've already talked about this expression. We have a squared here. All that means is that we're going to add a t to the time domain version of the expression. So we have t times 1/2 e to the negative 2t. And then let's go ahead and move this off to the right, times the unit step function. That's a negative sign, negative sign. Okay. So what are we missing? We're missing this guy on the left. And the reason why I saved him for last is because we need to use this general form of the expression. So, while we wait for it to load, so we have 1 over a plus j omega to the power of n. So we're just talking about some arbitrary, power here. And if we look over here on the left side, so if we're going in this direction with our Fourier transform to the left here, we can see that we end up with t to the n minus 1 over n minus 1 factorial, right? So the power of n in our case is 3. So that means that this becomes t squared over 2 factorial is just 2, because it's 1 times 2, and then e to the negative at ut. So the only thing that changed was this right here. And you can see that as your power goes up, the power here goes up. Just like how a t to the first power gives you a square, t squared, and let me draw that in a different color here to emphasize, t squared gives you this expression cubed, and so on and so forth. You just have to remember that arrow is pointing in the wrong direction. You got to remember this factorial on the bottom. That'll get you if you're not careful. So coming back here, we can see that this is the power of 3. So we end up with t squared over 2 factorial e to the negative 2t times the unit step function plus, because that's positive there. And that's it. This is the answer to B. This is your new y of t. And you can see again that without, we didn't do any advanced math here. It was all arithmetic. That's all we did. And again, this probably reminds you of differential equations. But the key thing to remember when you're doing this is that it's not hard. You just have to remember your relationships, and that sometimes it's easier to go into the time domain than it is to try to deal with convolution or it's easier to go to the frequency domain than it is to deal with convolution and whatnot in the time domain. It's not always simpler, but in the case of these differential equations, these LCCDEs, it tends to be. So, that's the answer. That's the answers. We got them both done. I hope this video helps you to understand how to solve this kind of problem. I know this won't help you with every kind of LCCDE problem, but it if you run into something that you want me to look at, or you want me to help, that you want me to solve, I'm always looking for new problems to solve. So just send me an email, leave a comment, let me know what it is you want me to do, and I'll try to do it for you. Or we'll do it together. How about that? We'll do it together. So, thanks a bunch, and good luck.